Let us now understand the work kinetic energy theorem from the perspective of a system. How do we interpret it in terms of systems? How do we use it with a system of particles? So to get there, let's first consider how to apply the work kinetic energy theorem with multiple particles. To do that, all you have to do is add up the work done by all the forces on each particle and add up all those works together, and that will be the total work done on all the particles. Or, as you can see below, what we do is we add up the net work done on object 1, we add up the net work done on object 2, and we add those together, and all the net work done on all the objects from I equals object 1 to object n, and we get the total work done on all the particles. We can do this because, remember, the work kinetic energy theorem holds for one particle, and then once you've added up all the work done on all the particles, you add up all the kinetic energy changes of all the particles. Or in math terms, it looks as follows. We add up the change in kinetic energy of object 1 to the change in kinetic energy of object 2. Then we add that to the change in kinetic energy of object 3, all the way up to object number n. And that is the total change in kinetic energy of all our particles. It's just the sum of the individual changes in kinetic energy of each individual particle. And then once we have that, we can have the work kinetic energy theorem applied to all these particles. The work kinetic energy theorem states for all these particles that the total work done that we calculated up here is going to be equal to the total kinetic energy change that we calculated over here. So add up all the works, and it's equal to the sum of all the kinetic energy changes of all the objects. Or to write it more shortly, work total equals the change in kinetic energy total. Why does this work? Well, remember the work kinetic energy theorem, it held for one particle. So if we have two particles, we can apply the work kinetic energy theorem to particle 1, and we can apply it to particle 2. And then once we do that, we can just add the two equations together, and that will result in the math below. And therefore, the total work done on all the particles will be equal to the change in kinetic energy of all the particles, the total change in kinetic energy. All right, now that we've done that, let's consider these objects in terms of systems. To think in terms of systems, let's consider the following example. We have a system of two blocks, so we're not including the Earth in this system, which makes gravity an external force, as well as the normal force from the ground on the blocks. And these blocks are being pushed by an external force F over here. And they're getting pushed to the right and are moving along to the right with some velocity v. Observe the following features. There is work done by objects that are inside the system. These two objects have contact forces that arise, normal forces, and they are Newton's third law of pairs. The force of block 1 on block 2 goes to the right, and the force of block 2 on block 1 goes to the left, which I'm calling N21 for force of block 2 on block 1, and N12 for force of block 1 on block 2. These forces are doing work because these objects move to the right, and these forces are parallel to the rightward direction. They're along the same axis, so they will do work. N12 does positive work, and N21 does negative work. So block 1 does positive work on M2, and M2 does negative work on M1. We see then that there is work done by objects in the system on each other. There is also work done by objects outside the system on the objects inside our system. This force F does work on block 1. So we have a force outside our system doing work on objects inside our system. Because there is work done on these objects, whether the work is done by forces and objects inside the system or by forces and objects outside the system, all of this is work being done on point particles. And so the work kinetic energy theorem applies to this system of objects. As the work is being done on the objects in the objects in the system undergo a change in kinetic energy. So how does the work kinetic energy theorem apply to the system? Quite simply, the net work done on the system is the change in kinetic energy of the objects of the system. How do we know that? Well, we know the work kinetic energy theorem applies to M1. The work kinetic energy theorem didn't say anything about whether the forces were inside or outside the system. So we add up all those forces, whether they're outside or inside the system, and that's the change in kinetic energy of block 1. And we do something similar for block 2. And by our reasoning just previously about multiparticles, if we add up all the work and get the total work done, we'll get the total change in kinetic energy, the sum of the change in kinetic energies of block 1 and block 2. So then, as you can see, to think in terms of systems, we need to think about the work done both by objects inside the system and by objects outside the system. And then we can apply our reasoning about the work kinetic energy theorem to multiple particles. When we talk about systems, we sometimes are a little bit vague about whether it's the objects that are gaining kinetic energy or it's the system that's gaining kinetic energy. The objects gain kinetic energy, but if those objects are inside our system, we usually say it is the system that is gaining kinetic energy. It is the system that undergoes a change in kinetic energy. And so what we have here then is the net work done on a system is the change in the system's kinetic energy, where by net work done on a system, we are including all the work done by objects inside the system also. As with both the single and multi-particle case, if positive net work is done, then kinetic energy is gained. If negative net work is done, then kinetic energy is lost from our system. We should think about work then as being something that either adds kinetic energy to our system or removes kinetic energy from our system. It is the way to add or remove kinetic energy from a system. In this example here, we would have as follows, or as I've already stated, we add up the work done by the force F, the work done by the two normal forces. We could add up the work done by gravity and the normal force, but those contribute 0 to the work done. And that will equal the change in kinetic energy of block 1 plus the change in kinetic energy of block 2. Or in other words, the total work done on the objects in our system is equal to the change in kinetic energy of the objects in our system. The net work done on the system, which includes work done by forces in the system, is equal to the change in kinetic energy of our system, the total change in kinetic energy of our objects. In general, then, we can write the work kinetic energy theorem for systems in a simplified form as net work equals change in kinetic energy, where now we understand net work to mean all the work done by objects in our system and all the work done by external forces on the objects in our system. We add it all up together, and then we add up all the changes in kinetic energy of all our objects in our system and set them equal to each other. And this will happen as the system changes from state A to state B. What do I mean by that? What I mean is our system has some initial state A, and as a result of all the internal forces and external forces, we reach a state B. At state B, our objects have undergone all sorts of various displacements from state A, and those displacements were due to the work done by all these forces that are acting on the objects. And so, because these displacements aren't necessarily the same for each of these objects, instead we speak of state A, our objects are here, and state B, they have all undergone various displacements from the various work done by the various forces into these positions over here. And so then the work done as a system changes from state A to state B is equal to the total change in kinetic energy of our objects as they change from state A to state B.